things just got a lot worse. 2 days ago, we covered a single CME headed for Earth, and apparently, that was just the opening shot. Since then, the same sunspot has fired 3 more times, and right now, 3 separate plasma storms are racing toward Earth, set to arrive over the next 48 hours, during the 1 week per year when Earth's magnetic shield is scientifically documented to be at its absolute weakest. This is not a forecast. This is already happening, and buried inside this sequence is a historical pattern connecting 5 solar maximums to 5 consecutive surges of global conflict across human history. Stay with us until the end. Because what this week actually means is something the headlines are not telling you. If this has you hooked, subscribe to the Skylab because solar maximum's not over. Active region 4392 is still on the disk, and we will be here tracking everything. Comment below and tell us what you actually think. 5 solar cycles, 5 surges of global unrest, 3 simultaneous CMEs arriving during Earth's weakest magnetic window. Is it just one big coincidence, or something the data is trying to say out loud? We genuinely want to know what you think. Now let's get into it. Part 1. This was never just one. They told you it was one event, one coronal mass ejection, one moderate flare, one story with a clear beginning and a tidy ending. They were wrong. Not because anyone lied, but because the sun had not finished speaking. 2 days ago, active region 4392 sent its opening shot toward Earth. A single coronal mass ejection, M-class flare, respectable but manageable. Scientists logged it, agencies issued their watches, the internet did its thing, half panic, half dismissal. And then, before the ink was even dry on those first reports, the same sunspot group fired again, and then one more time after that. 4 M-class flares in 6 days, 3 separate coronal mass ejections now in active transit toward Earth. Not one story, a series. And the distinction matters enormously, because we are not talking about 3 independent moderate events happening to occur close together. We are talking about a sequence with physics that change when you stack them. The sun did not send one punch, it sent a combination. Active region 4392 is the engine behind all of this. It is a sunspot cluster with what scientists classify as a beta-gamma magnetic configuration, which, in plain terms, means its magnetic field lines are tangled in a way that creates constant instability. Think of it like a rubber band twisted too many times. At some point, it snaps. The energy has to go somewhere. In the case of a sunspot, it goes into space as radiation and plasma, as flares and coronal mass ejections hurled outward at speeds that would make your head swim if you stopped to think about them. And here is what matters most about where this region currently sits on the solar disk. It is positioned at or near disk center, meaning it is facing Earth almost directly. When a coronal mass ejection is launched from a region that is pointing straight at you, the probability of a direct hit rises dramatically. This is not a glancing blow scenario. This is a head-on geometry, and that changes everything about what we can expect. So let us be precise about what is currently en route. The first coronal mass ejection was launched on March 16th, associated with an M2.7 flare, and it is moving fast, estimated at roughly 1,200 kilometers per second. The second was launched on March 17th, tied to a filament eruption, and it is slower. The third was launched on March 18th, another M2.7 flare, and it falls somewhere between the first two in terms of speed. 3 objects, 3 different departure times, 3 different velocities, all aimed at the same destination. The National Oceanic and Atmospheric Administration, NOAA, has issued a G2 geomagnetic storm watch running through March 21st. G2 is considered a moderate geomagnetic storm. That sounds reassuring, and in isolation it probably should be. But the watch also notes that G3 conditions, classified as strong, are possible when the final wave arrives, and there is a reason the forecast gets worse as it goes later. We will get to that. What you need to understand right now is that the conversation has already shifted. 48 hours ago, this was a single event story. Today, space weather agencies are tracking a compound sequence with overlapping arrival windows and uncertain interaction dynamics. The models are being updated in real time. The uncertainty ranges on arrival times are measured in hours, and when 3 objects are converging on the same destination with arrival windows that close, the margin for error shrinks fast. The KP index, a global measurement of geomagnetic activity on a scale from 0 to 9, is expected to reach 6 or 7. A KP of 5 is G1, a KP of 6 is G2, a KP of 7 is G3. These are not arbitrary numbers. Each step represents a measurable increase in the magnetic disturbance experienced at Earth's surface, in its upper atmosphere, and in the near space environment where our satellites live and work. NOAA's Space Weather Prediction Center does not issue G2 watches casually. They have data from coronagraphs, space-based instruments that block out the sun's face to photograph what is coming off its edges and surface. They have velocity estimates from radio bursts and satellite readings. They are watching these three objects cross the 150 million kilometre gap between the Sun and Earth in something close to real time, with the best tools humanity has ever built for this purpose. And they issued a watch anyway. There is no apocalypse incoming. Say that clearly and say it first. Your power grid is probably fine. Your GPS will likely give you minor headaches at worst. The northern and southern lights may be visible at unusually low latitudes, which is actually extraordinary if you get the chance to see them. But the reason this matters, the reason this is not just a space weather footnote, is what happens when you stop treating these three events as separate and start treating them as one compound sequence with compounding effects. Because the first wave may have already arrived, and if it has, then what comes next is arriving into an environment that is already disturbed, a magnetosphere already under pressure, a system that has already started to strain before the second hit, let alone the third. We have always thought of solar storms as events, discrete, measurable, singular. But what if the more dangerous version is not the biggest single impact, but the one that never stops coming? The first wave may have already begun. Part 2. The timeline. Nobody is showing clearly. Understanding what is happening requires you to stop thinking about these three coronal mass ejections as a group and start thinking about them as a sequence with its own internal logic, because the timing of each eruption and the gap between them determines everything about what Earth experiences when they arrive. March 16th. Active region 4392 produces an M2.7 flare. That is a moderately strong solar flare. Not the biggest category, but nothing to ignore either. The flare itself takes about 8 minutes to reach Earth at the speed of light. The associated coronal mass ejection, the actual cloud of magnetized plasma flung off the sun's surface, moves much slower, but still fast by cosmic standards. Estimates put this first ejection at roughly 1,200 kilometers per second. That is over 4 million kilometers per hour. A human-built spacecraft would take years to reach that speed. This cloud of plasma achieves it in minutes. Then March 17th. A filament eruption, a different type of solar event where a long arching structure of plasma that had been suspended in the sun's magnetic field becomes unstable and collapses outward. Filament eruptions tend to launch slower coronal mass ejections. This one does exactly that. It departs at a pace slower than the first, which means there is a real and calculable probability that the faster March 16th ejection will catch up to it somewhere between the Sun and Earth. Then March 18th, another M2.7 flare, another ejection. This one's speed falls somewhere between the first and second. Three objects departing roughly 24 to 48 hours apart, moving at slightly different velocities, through a medium, the solar wind, that is itself turbulent and variable. How do we know any of this? Primarily through a network of space-based instruments that most people have never heard of. SOHO, the Solar and Heliospheric Observatory, carries a coronagraph that has been watching the Sun from a fixed point between Earth and the Sun since 1995. Stereo satellites provide views from different angles. The Dieskova satellite, positioned at the first Lagrange point about 1.5 million kilometers from Earth, acts as an early warning sensor that measures solar wind conditions about 15 to 60 minutes before they actually hit Earth. Type 2 radio bursts are another key piece of evidence. When a coronal mass ejection moves through the solar corona fast enough, it generates a shock wave. That shock wave produces radio emissions at specific frequencies that drift over time in a characteristic pattern detectable from Earth-based radio observatories. Type 2 bursts were detected in association with these events. That confirms shock waves. That confirms the ejections were energetic enough to compress the plasma they moved through. Now, here is the part that makes forecasting genuinely difficult. Each of these three ejections, modelled on its own, would be considered a moderate event, G1 to G2 territory, standard solar storm response, satellites in safe mode for a few hours, maybe some GPS degradation, aurora visible down to mid-latitudes. Scientists would track it, write papers about it, and mostly move on. But they are not arriving in isolation. This is the critical fact that standard reporting consistently fails to communicate. When two coronal mass ejections are launched close together, with the second one moving faster than the first, something happens that changes the nature of both. The faster ejection begins to catch the slower one. As it closes the gap, the plasma fields begin to interact. The leading edge of the faster ejection compresses against the trailing edge of the slower one, creating a region of heightened magnetic field strength and plasma density. Scientists call this CME cannibalism or CME-CME interaction. The combined structure that results is not simply the sum of two separate events. It can be more energetically complex, carrying a stronger and more variable magnetic field than either ejection would have carried alone. The interaction changes the orientation of the magnetic fields within the combined structure, and that orientation, specifically whether the magnetic field is pointing southward when it hits Earth, is the single most important factor in determining how severe a geomagnetic storm becomes. A southward-pointing BZ, the component of the interplanetary magnetic field that most directly couples with Earth's own field, is like an open door. It allows solar energy to pour into the magnetosphere instead of deflecting around it. And the interaction between two merging coronal mass ejections can create southward BZ conditions that neither ejection would have created independently. The models can estimate arrival windows. They can approximate magnetic field strengths. What they cannot do reliably is predict BZ orientation far in advance. That value is often not measurable until the solar wind actually reaches DSCOVR, giving forecasters 15 to 60 minutes of warning before it hits Earth. In storm terms, that is barely enough time to blink. This is why the G2 watch comes with a G3 possibility. Not because scientists are being imprecise, but because they are being honest. 3 ejections, 2 of which may be merging in transit, arriving at an Earth whose space environment has been primed by elevated solar activity for days. We are not watching 3 separate events. We are watching them merge into something the models were not built to predict. Part 3, the stacking effect where forecasts break. Imagine you are holding a door shut against wind pressure. One gust hits. You hold. A second gust hits before you have fully recovered your footing. You hold, but barely. A third gust arrives before you have taken a single full breath. At what point does the door give? Not necessarily when any single gust is strongest, but when the gaps between them are too short for you to reset. That is the stacking effect. And it is where solar storm forecasting starts to quietly fall apart. Earth's magnetosphere is not a passive shield. It is a dynamic, responsive system that compresses under pressure, rebounds when pressure drops, and then, critically, requires time to recover before it can absorb the next impact efficiently. When a coronal mass ejection hits, the magnetosphere is compressed on the sunward side and stretched on the night side like a teardrop being pushed from the front. Energy pours in. Currents circulate through the upper atmosphere, the KP index rises. Eventually the storm subsides, the energy dissipates, and the magnetosphere begins to recover its baseline configuration. That recovery takes time, not hours, sometimes a day or more for a full reset. And this is where the stacking scenario becomes genuinely concerning. When the first ejection compresses the magnetosphere and the system begins to adapt, it is doing so in an already disturbed state. The second ejection does not arrive to a fresh, fully pressurized magnetic shield. It arrives to one that is already mid-recovery, already stressed, already running on what you might think of as reduced capacity. The third ejection, arriving as the system is still processing the second, encounters a magnetosphere that has now been under sustained pressure for an extended period. And sustained pressure is not the same as peak pressure. The KP index, which is reported as an average over 3-hour windows, can look moderate even when the actual real-time fluctuations are intense. You can have a storm that never technically reaches the highest alert levels, but maintains elevated activity long enough to cause effects that a shorter, sharper storm would not. This is the difference between a heavy rainstorm that passes in an hour and a steady, soaking rain that lasts 3 days. The peak intensity of the former might be more dramatic, but the latter saturates the ground, backs up drainage systems, and causes damage that the dramatic downpour never would, not because any single drop was harder, but because the system never got a chance to drain. Historically, the most damaging geomagnetic events are not always the ones with the highest peak CAPE. The March 1989 event that knocked out power to the entire province of Quebec did reach extreme levels, a KP of 9, but events at G3 and G4 that have persisted for 18 or more hours have caused satellite anomalies, navigation disruptions, and power system stress that shorter G5 events did not. Duration, it turns out, often matters more than magnitude. Modern power infrastructure, particularly high-voltage transmission systems, is remarkably efficient. It moves electricity across enormous distances with minimal loss. But that efficiency comes with a trade-off. Long transmission lines act as antennas for geomagnetically induced currents, or GICs. These are not the electricity the grid is designed to carry. They are slow, direct current surges induced by the rapid fluctuation of Earth's magnetic field during a storm. Transformers, the large, expensive, difficult-to-replace components that step voltage up and down across the grid, are particularly sensitive to these currents. They are designed for alternating current, not direct current intrusion. Sustained GIC exposure causes heating. Heating causes stress. Stress, over enough time, causes damage. The key phrase there is over enough time. A brief spike in GIC levels may trip automatic protection systems, causing temporary outages but avoiding permanent damage. A sustained period of elevated GICs, exactly what a stacking scenario with multiple arriving ejections might produce, is a different kind of test. The KP index alone does not capture this. Single event forecasts do not model this, and compound event scenarios are the ones the grid operators privately worry about most. This is also where the KP index as a communication tool shows its limits. Forecasters issue a G2 watch because their models, processing these events individually, produce outputs in that range. What the models do not yet do well is account for the nonlinear amplification that can occur when disturbances arrive in rapid succession. Energy input to the magnetosphere during compound events does not simply add, it can amplify, creating effects that exceed what any individual event in the sequence would have generated alone. Scientists know this. It appears in the research literature, but translating that uncertainty into public-facing forecasts is genuinely difficult, because saying G2 but possibly much worse is not a precise enough statement to be operationally useful. So the formal watch says G2, G3 possible, and everything that happens beyond that lives in the uncertainty margin, which is not nothing. Uncertainty is where surprises live. We are not measuring a storm, we are measuring a chain reaction. And chain reactions do not care what our models predicted. Part 4, the March 21st problem. Every storm has a worst moment. For this one, the models are pointing at March 21st. Not because that is when everything necessarily hits hardest, but because that is when the last piece of the sequence is expected to arrive, and it is not arriving alone. The third coronal mass ejection is forecast to reach Earth's vicinity in rough alignment with something called a coronal hole high-speed stream. And if that timing holds, the combination produces conditions that are meaningfully different from anything the first two waves generated independently. A coronal hole is exactly what it sounds like, a region of the sun's corona where the magnetic field lines are open rather than looped back into the surface. Open field lines allow solar wind to escape more freely and more quickly. The result is a stream of solar wind moving significantly faster than the average background wind, fast enough to compress the space environment ahead of it, and fast enough to arrive at Earth with its own elevated energy content. By itself, a coronal hole high-speed stream might produce a G1 or G2 geomagnetic storm, an event worth noting, not catastrophizing. But it is not arriving by itself. It is arriving in the wake of 2 or 3 coronal mass ejections that will have already disturbed the near-Earth environment. The magnetosphere will have already been worked over. The solar wind conditions ahead of the third ejection will already be elevated. And then this additional stream of fast solar wind effectively acts as a pressure sustainer, not a new impact, but a prolonged push that keeps the geomagnetic activity elevated well beyond where it would have dropped if the ejections had arrived without it. Here is something counterintuitive about geomagnetic storms that forecasters understand well, but public communication rarely captures. The most intense geomagnetic response does not occur at the moment of impact. It occurs afterward. When a coronal mass ejection arrives, the initial compression of the magnetosphere is measurable, but often not the worst part. The worst part tends to come during what is called the main phase of the storm. when the magnetosphere begins to respond to the sustained energy input, when ring current particles accumulate and circulation patterns establish themselves, when the full coupling between the solar wind and Earth's magnetic system comes into effect. This lag can be significant. The main phase of a major storm can develop hours after the initial shock arrival, which means that if the third ejection arrives on March 21st and produces a main phase that develops overnight into March 22nd, the time of peak geomagnetic impact may be well after the technical arrival that the forecast models time. The storm continues to unfold after the structure has passed. The aftermath is part of the event. The KP forecast for this period sits in the 6 to 7 range, G2 to G3 territory. That means radio blackouts possible at high latitudes, satellite orientation problems possible, voltage control problems on power grids in high latitude regions possible, aurora visible down to lower latitudes than normal. These are not catastrophic outcomes. They are measurable, real-world disruptions with operational consequences for specific industries and systems. The post-equinox timing also matters in a way that is not speculative, but documented in decades of satellite and ground-based magnetic data. The spring equinox creates conditions, which we will cover in the next part, that enhance the coupling efficiency between the solar wind and Earth's magnetic field. This means the same solar storm input can produce a stronger geomagnetic response during this window than it would during other parts of the year. So the third ejection arrives into a system that has been weakened by its predecessors, extended by a trailing high-speed stream, and amplified by the geometry of the equinox. The models show the impact, the models show the arrival times. What the models do not fully show is what the atmosphere looks like after everything has arrived and the system is trying to recover against sustained incoming pressure. That is the part that does not fit cleanly into a KP index reading. That is the part that happens after the charts say the event has passed. The real storm may begin after everything has already arrived. Part 5. The sunspot that will not stop. Active region 4392 is still there. That is the detail that should stay with you after everything else. While we track the 3 ejections already in transit, already crossing space toward us, the sunspot group that launched them has not finished. It is still on the disk. It is still classified as magnetically complex. And it has already demonstrated that it is willing to fire repeatedly. A sunspot is not simply a dark spot on the sun's surface, though it does appear darker in photographs because it is cooler than its surroundings, typically around 3,500 degrees compared to the sun's surface temperature of roughly 5,500 degrees. The darkness is a consequence, not the thing itself. The thing itself is a concentrated region of powerful tangled magnetic field that has punched through the sun's convective layer and locked the plasma in place, suppressing the normal circulation that brings heat to the surface. The magnetic classification of beta-gamma tells you something specific and important about the internal structure of the field in a given active region. Beta means there are 2 polarity regions, positive and negative magnetic poles, in the same active region. Gamma means the configuration is irregular, that you cannot draw a clean boundary between the 2 polarity zones. Beta-gamma combined means the field lines are not just adjacent, they are intermixed, twisted around each other, storing energy in their geometry, the way a coiled spring stores energy in its compression. When those field lines cross and reconnect, a process called magnetic reconnection, the energy stored in the magnetic topology is released almost instantaneously. That releases a solar flare. The radiation from the flare reaches Earth in 8 minutes. The associated plasma ejection follows over the next 1 to 3 days, depending on speed. The flare itself is the announcement. The coronal mass ejection is the consequence. 4 M-class flares in 6 days from the same region. That is a rate that tells you the region has not exhausted its stored energy. Each reconnection event releases some of that stored magnetic energy, but the sun continues generating and feeding energy into the sunspot's magnetic structure through the churning convective layer beneath it. It is not a battery that runs out. It is more like a generator with fuel still flowing. The disk center positioning matters enormously and deserves more explanation than it usually gets. The sun rotates, completing 1 full rotation in approximately 25 days at its equator, slightly slower at higher latitudes. As it rotates, active regions move across the visible disk from east limb to west limb, spending roughly 2 weeks crossing the Earth-facing hemisphere. When an active region is near disk center, ejections launched from it travel in the direction that most directly intercepts Earth's orbit. As the region rotates toward the west limb, ejections are increasingly launched at an angle, more likely to miss, or to deliver glancing blows rather than direct impacts. Active region 4392 is currently near disk center. That position is, statistically speaking, the worst place for Earth, the geometry that produces direct impact coronal mass ejections. It will rotate toward the west limb over the coming days, reducing but not eliminating the Earth-directed threat as it moves. But before it does, there is a window, perhaps 3 to 5 more days, in which it remains geometrically positioned to send ejections our way. Solar analysts currently assign approximately a 5% probability of an X-class flare from this region in any given day. That sounds small, it is not trivial. 5% per day, compounded over 5 days, gives you a roughly 23% cumulative probability. And an X-class flare, the highest category on the scale, from a disk center active region would produce a coronal mass ejection with significantly more energy than any of the 3 currently in transit. An X-class event from this position, and at this time during the equinox window, following a sequence that has already primed the space environment, would reset every assumption in this story. The 3 waves are already launched, but the gun is still loaded. If this region fires again before rotating out of position, this story does not end. It starts over from a higher baseline. Part 6. The Equinox Weakness Window. Twice a year, without fail, Earth's magnetic defences become measurably easier to breach. Not because anything visibly changes, not because the magnetosphere develops holes or weakens in any way you could point to on a diagram. The effect is subtler than that, but it is real, it is documented, and it has a name. The Russell-McFerran effect, first described in 1973 by Christopher Russell and Robert McFerran, and validated by decades of satellite data since. To understand why it happens, you need to understand a little about geometry. Earth's magnetic axis is tilted relative to its orbital plane around the Sun. The Sun has its own magnetic equator, which is itself tilted slightly relative to the ecliptic, the plane of Earth's orbit. These 2 tilts create a twice-yearly alignment condition in which the orientation of the solar wind's magnetic field most efficiently couples with Earth's own magnetic field. The coupling mechanism comes down to a quantity called BZ, the north-south component of the interplanetary magnetic field carried by the solar wind. When BZ is pointing southward, opposite to the direction of Earth's magnetic field lines at the dayside magnetopause, the 2 fields can reconnect. That reconnection is the mechanism that allows solar wind energy to transfer into Earth's magnetosphere. A northward BZ deflects. A southward BZ opens a channel. Think of it as a key turning a lock. The field orientation is the key, and the Russell-McFerran effect is the seasonal reason the lock is easier to turn. Near the equinoxes, roughly March and September, the geometric alignment of Earth's magnetic axis relative to the solar wind flow maximally favours southward BZ coupling. Studies analysing decades of geomagnetic storm records consistently show a roughly 40% increase in storm energy input during the equinox windows compared to solstice periods. Geomagnetic storm frequency approximately doubles. Events that might have been G1 storms at a different time of year become G2 events. G2 events shade toward G3. This is established physics. It is not theory or hypothesis. It is a pattern identified in the data, explained by orbital geometry, and reproducible across multiple solar cycles. Researchers use it when modelling long-term geomagnetic storm statistics. Power grid operators in high-latitude regions know about it. It is simply not something that makes it into mainstream space weather reporting, because nuanced seasonal effects are harder to communicate than peak storm ratings. The equinox is March 20th. The 3rd coronal mass ejection is expected to arrive around March 21st. The coronal whole high-speed stream is expected in the same window. The Russell-McFerran effect peaks in the days just after the equinox, not precisely on it, but in the period when the geometric alignment is most favourable for enhanced coupling. March 21st sits almost perfectly inside that window. This is not coincidence in a conspiratorial sense, it is coincidence in a purely astronomical sense. The Sun does not know what day it is on the human calendar. The equinox does not warn the Sun to hold its fire. What we are dealing with is an overlap of 2 independent phenomena, a solar storm sequence and an annual geometric effect, that happen to be reaching their respective peaks at the same time. That overlap has real, calculable consequences. Earth's magnetic shield is not gone. The magnetosphere is still there, still deflecting the vast majority of solar wind around the planet, still doing what it has done for billions of years. But during the equinox window, the efficiency with which incoming solar energy couples into that system is measurably elevated. More energy gets in. More energy means stronger geomagnetic response. Stronger response means more disruption to satellites, navigation, power systems, and radio communications. The shield is not down, but it is easier to get through right now than it will be in June or December, and this storm is arriving at exactly that moment. Not by design, not by pattern, just physics, colliding with timing, producing a window that forecasters are watching very carefully indeed. Part 7. Why this storm might overperform. There is a concept in space weather science called preconditioning. It does not get much attention in public space weather reporting because it is subtle and technical and does not translate easily into the kind of simple alert language that storm watches and KP index numbers provide. But it is one of the most important factors determining how a particular storm sequence actually behaves when it arrives, and it is directly relevant to what is happening this week in ways that the headline numbers do not capture. Preconditioning refers to the state of the near-Earth space environment before a new disturbance arrives. The magnetosphere is not a static shield that either holds or fails in binary fashion. It is a dynamic system with memory, a system whose current state depends on its recent history, on what it has absorbed and how much time it has had to recover. A magnetosphere that has processed a significant coronal mass ejection and returned to full baseline configuration responds to the next incoming event very differently than one that absorbed that same ejection 48 hours ago and has not yet completed its recovery. The second scenario has already been worked over. Its energy storage capacity is partially occupied, its dissipation mechanisms are running at elevated rates, its geometry, the configuration of field lines, current systems, and plasma populations, reflects a system that is mid-recovery rather than fully reset, and into that mid-recovery state the next event arrives. The space environment heading into this week was not quiet even before active region 4392 produced its first significant eruption. This matters and deserves emphasis, because the standard narrative of a solar storm event begins with the eruption and treats everything before it as background. The background this week was not background in the ordinary sense. Elevated electron flux, measurements of high-energy electrons trapped in Earth's radiation belts, were running above typical baseline levels before the first coronal mass ejection launched. The proton environment had been disturbed by earlier, smaller flare activity from multiple solar sources in the days preceding the main sequence. The solar wind arriving at Earth's magnetopause was already carrying an elevated particle density from activity that did not make significant headlines, but was nevertheless depositing energy into the system. This is not unusual during solar maximum. The background level of solar activity is elevated across the board during the peak years of the cycle, and quiet periods between events are shorter and less complete than they would be during solar minimum. But it means that the magnetosphere encountering the first coronal mass ejection from 4392 was not starting from a fully rested baseline. It was starting from a state that was already slightly depleted, already slightly elevated in its internal energy content, already primed in ways that the standard pre-storm KP index reading of near zero did not fully reveal. The elevated electron flux deserves specific attention because its consequences are not immediately obvious and are frequently overlooked in storm impact assessments. High-energy electrons, particles accelerated to energies of hundreds of kiloelectronvolts to several megavolts during geomagnetic activity, are the primary driver of the internal charging hazard for satellites that we discussed in detail in the previous part. Electron flux levels in the range of roughly 3,000 particle flux units, which is what the environment heading into this week was showing, represent a significantly elevated baseline. These electrons are already penetrating satellite structures, already accumulating charge in insulating materials, already advancing the population of spacecraft toward the internal discharge thresholds that produce anomalies. When the geomagnetic storm sequence then drives additional electron acceleration, as major storms reliably do, through the wave-particle interactions and injection events that characterize storm-time magnetospheric dynamics, the electrons being added to the radiation belt environment are arriving into a population that is already elevated. The combined effect produces higher peak electron energies and fluences than the storm alone would have generated from a quiet baseline. The satellite risk from internal charging is correspondingly higher than a simple assessment of storm magnitude would suggest. Magnetospheric fatigue is not a term you will find in the official scientific literature under that label. It is a descriptive concept rather than a formally defined quantity, and it is offered here as an analogy rather than a technical specification. But it describes something that is real, and that has real consequences. Large magnetic systems subjected to repeated, sustained energy inputs without adequate recovery intervals between them do not respond to each successive input identically. The energy storage and dissipation mechanisms within the magnetosphere, the ring current that encircles Earth and stores the energy injected during storm main phases, the substorm cycle that releases stored tail energy into the ionosphere, the plasmasphere that refills gradually after storm-driven erosion, all of these systems have characteristic timescales for recovery that range from hours to days. When new energy arrives before those timescales have elapsed, the systems are processing two or more events simultaneously, rather than sequentially. The efficiency of energy dissipation changes, the spatial distribution of effects changes, the relationship between incoming solar wind energy and resulting geomagnetic disturbance, a relationship that the KP index is designed to summarize, shifts in ways that the index, averaged over 3-hour windows, does not fully capture. Substorms are the most frequent manifestation of this dynamic during sustained storm sequences. A substorm is an internal magnetospheric event in which the stretched, energy-laden magnetic field of Earth's night-side magnetosphere, the long tail pointing away from the Sun, becomes unstable and rapidly collapses, releasing stored magnetic energy explosively into the ionosphere as auroral displays and electrical currents. Under quiet conditions, substorms occur perhaps once or twice per day. During active storm periods, they can occur every hour or two. Each substorm represents a pulse of energy deposited into the upper atmosphere, a surge of current through the ionospheric current systems that affect radio wave propagation, and a reconfiguration of the magnetospheric field geometry that temporarily changes the system's response characteristics. A sustained sequence of substorms driven by the prolonged energy input of 3 successive coronal mass ejections and a trailing high-speed stream is qualitatively different from the substorm activity associated with a single shorter event. It maintains elevated ionospheric currents for longer. It produces more total energy deposition into the upper atmosphere. It sustains the conditions for high-frequency radio disruption for longer intervals, and it does all of this at KP levels that the 3-hour average index describes as moderate. The comparison between a single intense brief storm and a sustained moderate one is worth dwelling on, because it cuts against the intuition most people bring to thinking about storm severity. Imagine 2 scenarios. In the first, a single G4 storm, a strong storm, KP of 8, strikes and passes over the course of 6 hours, after which conditions rapidly improve. In the second, a sustained G, 2 to G3 storm, moderate to strong, CAPE of 6 to 7, persists for 36 hours with only partial recovery intervals between successive disturbances. The peak intensity in the first scenario is considerably higher. The KP number is larger, the alarm level is higher, the headlines are more dramatic. But the total energy deposited into the magnetosphere over the full event duration in the second scenario may be comparable to or greater than the first, because integration over time compensates for lower peak rate. And the practical consequences, the ones that matter to the engineers and operators managing real infrastructure, skew heavily toward the sustained scenario. Satellite operators managing spacecraft in radiation-sensitive orbits are not most concerned about the peak radiation level during a storm. They are concerned about total radiation dose, the cumulative exposure integrated over the storm duration. A shorter intense storm and a longer moderate storm can produce similar total doses with very different peak rates. Power grid operators managing transformer thermal stress are not most concerned about the peak geomagnetically induced current level. They are concerned about how long elevated currents persist, because transformer heating is a cumulative process. Airlines routing transpolar flights around particle radiation exposure are not making decisions based on instantaneous radiation rates, but on projected total exposure for flight durations that can be 12 hours or more. In every case, duration competes with magnitude as the operationally relevant metric. In every case, the headline KP number, which emphasizes peak intensity over sustained duration, tells only part of the story. The forecasters at NOAA's Space Weather Prediction Center when they issue a G2 watch with G3 conditions possible, are doing exactly what good forecasters do. They are communicating their best estimate with honest representation of its uncertainty. That uncertainty is not a gap in competence, it is a property of the problem. Compound solar storm sequences involving CME interaction dynamics, equinox window coupling amplification, elevated pre-existing electron flux, and trailing coronal whole high-speed streams represent a configuration of simultaneously occurring factors that is genuinely rare in the historical record of well-instrumented events. The comprehensive satellite measurement era extends back to roughly the 1960s, 6 decades, 5 complete solar cycles, a limited sample of major compound events. Statistical models built on limited samples produce extrapolations with wide confidence intervals. The forecasters are not hiding uncertainty, they are accurately representing it, which is the most honest thing a forecaster can do. What this week's storm needs to cause meaningful, real-world effects across multiple infrastructure systems simultaneously is not extreme peak intensity. It does not need to reach G4 or G5. It does not need to produce the kind of cascade failure that generates power outage news coverage. It needs to arrive into a preconditioned system. It needs to involve 3 successive disturbances with insufficient recovery intervals between them. It needs to coincide with the equinox coupling window. It needs to be accompanied by a trailing high-speed stream that extends the disturbance period beyond what the ejections alone would produce. It needs, in short, to be exactly what it is. Not the biggest storm in the satellite era, but a sustained, compounding, poorly timed sequence that stresses systems designed for typical events rather than atypical combinations. Duration is the variable the models underweight. Duration is the variable that infrastructure operators privately find most concerning. Duration is what separates a storm that stresses systems temporarily from one that leaves marks that are only discovered later. This storm does not need to be extreme. It just needs to last, and right now, it is lasting. Part 8. The satellite risk nobody talks about. Most of the conversation about solar storms focuses on the things you can see, aurora spreading across the night sky at latitudes where it has no business appearing, visible to people who have never seen it before and will describe it for the rest of their lives. Power outages, if the storm is severe enough. The kind of infrastructure failure that generates news coverage and emergency response and congressional hearings. Radio blackouts, GPS degradation, compass anomalies. These are visible, reportable, relatable consequences. They translate into headlines and social media posts and dinner table conversations. They are the public face of space weather. But there is an entire category of solar storm consequence that almost never makes the news. That unfolds silently, over days and sometimes weeks, in systems that most people interact with constantly without ever thinking about where those systems actually live. It is consequence that is managed by small teams of engineers in operations centres that the public has never heard of, logged in anomaly reports that are never published, priced into insurance actuarial tables that are never discussed outside the aerospace industry. It is the satellite risk, and it is, in terms of its aggregate economic and operational significance to modern civilization, arguably more important than any of the visible effects, and it barely registers in public awareness. Start with the scale of what is currently operating above your head, because the numbers have changed dramatically, and most people's mental model has not kept pace. There are currently more than 10,000 active satellites orbiting Earth, 10,000 functioning machines, each one representing years of engineering effort and hundreds of millions to billions of dollars of investment, circling the planet continuously in orbits ranging from a few hundred kilometers altitude in low Earth orbit to 36,000 kilometers at geostationary distance. That number has roughly tripled in the last 5 years. The driver is primarily the deployment of large commercial broadband constellations, the satellite internet services that are extending high-speed connectivity to remote regions, maritime routes, polar areas, and anywhere else that ground-based fiber and cellular infrastructure has not reached. Each constellation requires hundreds to thousands of satellites to provide the coverage density its service model demands. Several are already partially operational, several more are in development. The trajectory points toward 100,000 operational satellites within a decade, a number that would have seemed like science fiction 10 years ago and is now a plausible engineering projection. Every one of those 10,000 current satellites is operating in a radiation environment that a geomagnetic storm actively disturbs. Every one of them is being monitored by someone right now during this storm sequence, watching telemetry for the signatures of anomalous behaviour. The monitoring is continuous, the anomaly thresholds are carefully calibrated, and the response procedures are well practiced. But the hazards are real, and they operate through mechanisms that are worth understanding in detail because they are so different from the visible drama of aurora and power outages. Surface charging is the more straightforward of the two primary electrical hazard mechanisms that solar storms create for satellites. When a geomagnetic storm drives high-energy plasma into the near-Earth environment, that plasma interacts with satellite surfaces. Charged particles, electrons and ions, arrive at the satellite's exterior and deposit charge on whatever they contact. Solar panels accumulate charge, thermal blankets accumulate charge, structural surfaces accumulate charge. This would be manageable if the entire satellite accumulated charge uniformly, because a uniformly charged object simply sits at an elevated potential relative to its surroundings without experiencing internal stress. The problem is that satellites are not uniform objects. They are assemblages of different materials with different electrical properties, moving through plasma environments that vary in density and composition as the satellite orbits. Different parts of the satellite accumulate charge at different rates. Potential differences develop between adjacent surfaces. When those potential differences become large enough, and the thresholds are lower than you might expect because space is an excellent insulator and charge has nowhere to leak away, a discharge occurs, not a gradual equalization, a sudden, localized discharge, essentially a miniature lightning bolt between two adjacent spacecraft surfaces. The energy released in that discharge is deposited directly into whatever is nearby. If it is a solar panel junction, it can damage the panel's electrical output. If it is near an antenna feed, it can corrupt the signal. If it reaches sensitive electronics, it can flip memory bits, reset processors, or in severe cases cause permanent component failure. Satellites are designed with surface charging in mind. The choice of materials, the grounding architecture, the conductive coatings on certain surfaces. But design mitigation is not elimination. During active storm periods, surface charging events increase in frequency, and the anomaly logs fill with entries that engineers review and categorize and address. Internal charging is where the story becomes more insidious, because internal charging is not only more damaging than surface charging, it is delayed. The high-energy electrons that drive internal charging are not the lower energy particles that dominate surface charging. They're energetic enough, typically in the range of hundreds of kilo-electron volts to several megavolts, to penetrate through the satellite's exterior structure entirely and deposit their charge inside the spacecraft body, in the insulating materials surrounding circuit boards, in the dielectric materials of coaxial cables, in the backing materials of solar panels, in the housings of electronic components. These electrons do not discharge immediately upon arrival. They accumulate gradually over hours to days, building charge in insulating materials that have no easy path to ground. The charge continues to build until it reaches a threshold at which the insulating material can no longer contain it. Then it discharges, internally, directly into the circuitry surrounding it. The results of internal discharge range from recoverable to catastrophic. A single bit flip in a memory system is annoying and requires a reset but causes no permanent damage. A discharge that delivers energy to a voltage regulator or a signal processor can cause permanent component failure. A discharge into a power system component can cascade into a broader electrical fault, and the timing of the failure, which occurs not during the storm peak but hours to days after, when the accumulated charge finally reaches its discharge threshold, means that the connection to the storm is not always obvious. A satellite experiences a component failure on a Tuesday. The storm peaked on the previous Saturday. Was the failure caused by internal charging during the storm? By a manufacturing weakness that would have failed eventually anyway? By cosmic ray damage accumulated over months? Without real-time internal charging monitors, which most commercial satellites do not carry because they add mass and cost and complexity, the attribution is statistical rather than confirmed. The aerospace industry knows that storm periods correlate with elevated anomaly rates. The link for any specific failure on any specific satellite is often genuinely uncertain. The atmospheric drag consequence operates on a different timescale and affects a different population of orbital objects but it is in some ways the most broadly impactful of the three mechanisms during a sustained storm sequence. The atmosphere does not end at a defined altitude. It thins continuously with increasing altitude, transitioning through the stratosphere and mesosphere and thermosphere and exosphere in a gradient that extends well into what we call low Earth orbit. The thermosphere, the atmospheric layer that occupies the altitude range where most low Earth orbit satellites operate, is directly heated by the energy input of geomagnetic storms. Solar ultraviolet and X-ray radiation heats the thermosphere during flares. The particle precipitation and current systems of geomagnetic storms heat it further. As it heats, it expands. The altitude at which the atmospheric density reaches any given value rises. A satellite orbiting at 400 kilometers altitude suddenly finds itself in air that is measurably denser than it was before the storm, because the atmosphere has expanded upward to meet it. Denser air means more drag. More drag means faster orbital decay. A satellite that was losing altitude at a predictable, modelled rate before the storm is now losing altitude faster than its orbital maintenance models predicted. It needs to fire its thrusters sooner and more often than planned to maintain its operational orbit. Propellant is consumed, and propellant, as discussed in the context of this week's storm, is the finite resource that determines satellite operational lifetime. Every unplanned thruster firing during a storm period is a small but real reduction in how long that satellite will remain operational. Across a constellation of thousands of satellites, that aggregate propellant consumption has meaningful economic consequences that translate directly into accelerated replacement schedules and increased launch costs. The debris environment complicates this further. The 40,000 tracked pieces of space debris in low Earth orbit experience the same increased drag that operational satellites do, but debris cannot fire thrusters. Its response to the changed atmospheric conditions is entirely governed by physics, and the resulting orbital changes deviate from the pre-storm predictions that feed conjunction analysis systems. The calculations that tell satellite operators whether their spacecraft is at risk of collision with a tracked debris object become less precise during storm periods, because both the satellite's position and the debris object's position are evolving in an atmosphere that is behaving differently than the models assumed. Safety margins narrow, conjunction warning rates increase, operators maneuver more conservatively, consuming more propellant to maintain separation from debris whose position has become less certain. All of this is happening right now, above your head, managed by people whose job titles most of the public has never encountered. Satellite operations engineers, space weather coordinators, conjunction analysts, orbital mechanics specialists. They are watching telemetry, assessing anomalies, making propellant budgeting decisions, issuing maneuver recommendations, filing anomaly reports that will be reviewed in post-storm analysis and contribute to the industry's collective understanding of what this storm sequence actually cost. The biggest effects of this week's storm will not appear in photographs of the sky. They will appear in anomaly logs and propellant consumption reports and actuarial analyses conducted months from now. They will be real, they will be significant in aggregate, and they will be almost entirely invisible to everyone who is not specifically paid to notice them. They are happening right now, above your head, in the dark. Part 9. The Solar Maximum Pattern. There is a pattern that some researchers noticed a long time ago, and that mainstream science has treated with appropriate caution ever since. It is the kind of pattern that makes you uncomfortable precisely because it keeps showing up. Not once, not twice. But across centuries of human history, across different continents, different languages, different political systems, different centuries, the same correlation appears quietly in the data. And it is this. Periods of heightened solar activity, solar maximum, the peak of the sun's 11-year cycle, appear in the historical record to correlate with periods of heightened human conflict, social upheaval, and geopolitical instability. Say that slowly and carefully, because it is easy to say it wrong. The claim is not that the sun causes wars. The claim is not that sunspots make people angry, or that a flare in the corona somehow programs world leaders to make worse decisions. The claim is subtler and, in some ways, more unsettling than that. It is simply that when you overlay centuries of conflict data against solar cycle data, the peaks line up with a consistency that is statistically awkward to dismiss and scientifically difficult to explain, not every time, not with perfect precision. but enough that serious researchers have published papers about it, and enough that the dismissal of the pattern requires as much intellectual effort as the acceptance of it. Alexander Chizhevsky was a Russian scientist working in the early 20th century who is most associated with this hypothesis. He was by any measure a remarkable and unusual figure, a scientist, a poet, and a painter who believed that the cosmos and human civilization were not as separate as the modern scientific worldview assumed. He compiled historical records of wars, revolutions, epidemics, and mass migrations across multiple centuries and multiple civilizations, working through archives that covered roughly 2,400 years of documented human activity. Then he compared the chronology of those events to the solar cycle record. What he found was not a perfect one-to-one correspondence. It was something more like a gravitational pull, a tendency for the worst moments in human collective behavior to cluster around the years of solar maximum, and for relative calm to be more common during the years of solar minimum. His conclusion, published in the 1920s and largely suppressed during his later life under Soviet authorities who found it politically inconvenient, an irony that deserves a moment of quiet appreciation, was that human mass behavior appeared to correlate with the solar cycle. Periods of social calm roughly corresponding to solar minimum, periods of unrest, conflict, revolution, and collective agitation clustering around solar maximum. He was not saying that individual people were controlled by the sun. He was saying that populations, in aggregate, showed something like a mood cycle that tracked the solar cycle. That the sun was not the author of human history, but perhaps something closer to a seasonal influence on the conditions in which human history unfolded. His proposed mechanism was electromagnetic in nature. The idea that heightened solar activity, the increased flux of charged particles, the stronger and more variable geomagnetic environment, the elevated ultraviolet and X-ray output, somehow affects the central nervous system at population level. That it alters mood, increases irritability, lowers thresholds for confrontation, makes large groups of people more reactive and more susceptible to the kind of collective emotional states that historically precede violent conflict. Mass movements, he argued, required not just a political cause but a certain psychological kindling, a readiness in the population to ignite, and the sun, he believed, helped provide that kindling during its active periods. This mechanism remains scientifically unvalidated. That is the honest statement, and it matters. There is no demonstrated biological pathway by which solar electromagnetic changes reliably alter human neurological function in a population scale, behaviorally significant way. Studies looking for direct correlations between geomagnetic activity and psychiatric admissions, between solar flare days and aggression metrics, between KP index readings and documented conflict initiation, have produced mixed results at best. Some find weak correlations, others find nothing. The replication record is inconsistent. Chizhevsky's hypothesis has not entered the scientific mainstream precisely because the mechanism is missing. Without a mechanism, a pattern is just a pattern. But the pattern is still there, and it keeps showing up in the modern record, not just in the ancient archives Chizhevsky combed through. Solar Cycle 19, which peaked in 1958, encompassed the Korean War aftermath, the Hungarian Revolution, the Suez Crisis, and the beginning of the sustained nuclear confrontation between the United States and the Soviet Union that would define the next 3 decades. Solar Cycle 21, peaking around 1980, coincided with the Soviet invasion of Afghanistan, the Iranian Revolution, the outbreak of the Iran-Iraq War, and widespread civil conflicts across Central America and Africa that claimed hundreds of thousands of lives. Solar Cycle 23, peaking around 2001, included the September 11th attacks and the beginning of what became the global war on terror, reshaping the political geography of the world in ways still unfolding today. Solar Cycle 24, a weaker cycle that peaked around 2014, saw the Arab Spring's aftermath cascade into prolonged instability, the annexation of Crimea, the rise of the Islamic State across Syria and Iraq, and the beginning of the Syrian civil conflict that produced one of the largest refugee crises since the Second World War. Solar Cycle 25, the current one, began its rise around 2020. That year does not need additional annotation. What followed it in 2021, 2022, 2023, and 2024 does not need a list. Correlation is not causation. Say it again, firmly, and mean it every time you say it. These cycles overlap with human history in ways that could reflect coincidence or selective pattern matching. the deeply human tendency to find signal in noise, because our brains are built to find patterns even when patterns are not there. They could reflect the simple fact that conflict is a near-constant feature of human civilization, and will naturally appear in any period you examine closely enough. You could draw a circle around any 11-year window in the last 500 years and find wars, revolutions, and upheavals inside it, because there have almost always been wars, revolutions, and upheavals somewhere on Earth at any given time. Critics of the Chizhevsky hypothesis make all of these points. They are valid points. They deserve to be taken seriously before reaching any conclusion. But here is what makes the pattern genuinely uncomfortable, rather than merely interesting. It is not that any single solar maximum correlates with any single conflict. It is the consistency across 5 consecutive cycles, across different geographies, different political systems, different ideological contexts, different centuries in the case of the original historical record. The Korean War and the rise of Islamic State have nothing in common politically. The Iranian Revolution and the September 11th attack share no common origin. The Suez Crisis and the annexation of Crimea were generated by entirely different geopolitical dynamics, and yet all of them cluster inside the elevated activity portion of their respective solar cycles. 5 cycles, 5 surges, each with its own distinct causes, its own cast of historical actors, its own specific grievances and triggers, and the Sun, cycling through its magnetic activity with complete indifference to human affairs, peak after peak after peak, while history below produces its recurring upheavals in the same rhythm. The current solar cycle, cycle 25, is performing above predictions. This is documented fact, not interpretation. When the cycle was forecast at its inception, models suggested it would be a moderate cycle, perhaps similar to the relatively quiet cycle 24 that preceded it. Those predictions have not held. Cycle 25 has been more active than anticipated. Sunspot numbers have exceeded forecast values. The rate of significant flare activity has been elevated. Active regions have been more numerous and more energetic than the baseline models suggested they would be, and we are currently at or approaching the solar maximum of this cycle, the peak before the long decline back toward the relative quiet of solar minimum years from now. What that means in purely physical terms is clear. More flares, more coronal mass ejections, more geomagnetic storms, more disruption to satellites and navigation and power systems over the next year or two before activity begins to ease, that is certain. What it means in the context of Chizhevsky's pattern is something each person has to decide for themselves, because science has not decided for us. The correlation exists. The mechanism remains unproven. The history is what it is. You are living through solar cycle 25's maximum right now. This week, 3 coronal mass ejections from a single active region are converging on Earth during the one window per year when the magnetosphere couples most efficiently with incoming solar energy. The Sun is producing events at a rate that exceeded its own predicted schedule, and the world, as you are no doubt aware, is not experiencing a period of unusual calm. That is simply an observation. What you do with it is entirely up to you. If it is coincidence, it is a very consistent one. Part 10. External amplifiers. There is a comet, designated C/2026A1, informally called MAPS, and it is currently performing a close approach to the Sun that, under normal circumstances, would be a modestly exciting item in the astronomy news cycle. A sungrazer, or near-sun grazer, on an orbit that brings it within a small fraction of the Earth-Sun distance at perihelion, the closest point in its long journey around the star at the centre of our solar system. As it approaches, solar radiation and the solar wind are heating and ablating its surface with extraordinary violence, vaporizing ice and rock that may have been frozen since the earliest period of the solar system's formation, releasing a cloud of gas and dust that stretches into a tail millions of kilometers long. Comet MAPS is, in one sense, dying in slow motion as it rounds the Sun. In another sense, it is putting on the most dramatic performance of its 4 billion-year existence. Most sungrazers do exactly this and nothing more. They fall inward, they heat up, they develop spectacular tails, they round the Sun, and if they survive perihelion without fragmenting, many do not, they begin the long journey back outward into the cold. They are beautiful, they are ancient. They are, in the conventional understanding, passive participants in the physics of orbital mechanics, falling through the solar system on trajectories determined billions of years ago, carrying no influence on the star they briefly visit. This would be merely interesting astronomy, worth watching, worth photographing, worth a paragraph in the science section, except for a fringe hypothesis that has circulated in solar physics discussions for decades and refuses to fully go away despite the considerable skepticism directed at it. The hypothesis is this: large comets making close approaches to the Sun can perturb solar activity, that the introduction of a significant mass of cometary material into the solar corona, or the gravitational perturbation of a large object passing in close solar proximity, can in some way trigger or enhance flare activity and coronal mass ejections, that the Sun, in other words, is not entirely immune to what passes through its neighbourhood, that a visitor of sufficient size on the right trajectory might nudge the most powerful object in the solar system into behaviour it would not otherwise have exhibited at precisely that moment. The scientific consensus on this hypothesis is clear, and it should be stated plainly: it is not demonstrated. There is no confirmed mechanism by which a comet could reliably trigger solar flares. The mass of even the largest comets is trivially small compared to the Sun. We are talking about the difference between a grain of sand and a continent, and even that analogy flatters the comet. Gravitational effects of a comet on the Sun's interior dynamics are negligible by any calculation. The amount of material a comet actually deposits in the solar corona during a close passage is minuscule compared to the existing plasma environment, which contains more mass and energy than any cometary contribution could meaningfully disturb. Researchers who have specifically looked for statistical correlations between sun-grazing comet perihelion events and subsequent increases in solar flare activity have found results that are, at best, inconclusive and in many cases simply negative. The data does not support the hypothesis at the level required for scientific acceptance, and yet there is a reason this hypothesis keeps circulating, and the reason is not that fringe science enthusiasts refuse to accept the evidence. The reason is that several researchers, publishing in peer-reviewed journals, working with real data, using legitimate methodology, have noted specific instances in which significant flare activity followed cometary perihelion events by intervals that seemed shorter than you might expect from pure chance. The studies are methodologically disputed. The sample sizes are small because large sungrazers making very close perihelion passages are not common events, and the instrumental record of both comet passages and solar flare activity with sufficient overlap is limited to the last few decades at most. The conclusions drawn from these studies are contested by other researchers who find the statistical evidence unpersuasive. But the papers exist, the observations exist, and the question they are trying to answer, can something external to the Sun influence its behaviour, is not inherently absurd. It is a legitimate scientific question that has not been definitively closed. Consider what we already know the Sun responds to from outside itself. The tidal forces exerted by Jupiter, the most massive planet in the solar system, are measurable in solar rotation data. Jupiter's gravitational influence is real and detectable, even if its effect on solar eruptions is not established. The heliospheric current sheet, the vast warped surface in the solar wind where the Sun's magnetic polarity reverses, shifts in response to the positions of the planets as the solar system moves through space. The Sun does not exist in a vacuum of its own making. It sits at the centre of a gravitational and electromagnetic system involving 8 planets, countless smaller bodies, and a continuous flow of interstellar material. The idea that all of this leaves the Sun's behaviour entirely unchanged is not obviously correct. It is simply the current working assumption, because the evidence for significant external influence has not yet cleared the bar required for scientific consensus. The planetary alignment discussion extends this question further. There are periodic claims, from researchers operating well outside the mainstream and occasionally from ones operating closer to its edges, that the geometric alignment of the major planets exerts a gravitational and magnetic influence on the Sun sufficient to affect the timing or location of solar activity in measurable ways. Some variants of this hypothesis focus not on direct gravitational pulls, but on something called the Barycenter, the common centre of mass around which the Sun and all the planets orbit together as a system. The solar system does not orbit around the centre of the Sun. It orbits around the barycenter of the entire system. And when Jupiter and Saturn are on the same side of the solar system, which occurs on a roughly 20-year cycle, the barycenter actually lies slightly outside the Sun's photosphere. The Sun itself traces a complex looping path around this moving point, driven entirely by the gravitational choreography of the planets it hosts. Whether that motion, that constant, subtle, gravitationally driven displacement, has any effect on the Sun's internal dynamics, on the convective flows that generate its magnetic field, on the timing or location of eruptions from active regions is unproven, but it is not unstudied. There is a body of literature on solar-planetary interactions that sits in an uncomfortable position, too methodologically serious to dismiss as pure pseudoscience, too statistically weak to accept as demonstrated science. The honest framing of all of this is not that we have discovered comets control the Sun, or that planetary alignments schedule solar flares like items on a calendar. The honest framing is more modest and more interesting than either of those extremes. It is that we have genuine unresolved questions about external influences on solar behaviour, and the data available to answer those questions rigorously is limited by the relatively short period of high-quality instrumental observation. Science is filled with phenomena that spent years or decades in the category of fringe speculation before the mechanism was identified and the hypothesis was accepted. Ball lightning was considered a myth by many physicists until high-speed cameras captured it repeatedly. Prions, the misfolded proteins responsible for diseases like Creutzfeldt-Jakob, contradicted the established understanding of how infectious agents work, and their discoverer was widely dismissed before winning the Nobel Prize. The role of the bacterium Helicobacter pylori in causing peptic ulcers overturned decades of medical consensus that ulcers were caused by stress and diet, and the researchers who proposed the bacterial hypothesis faced sustained institutional resistance before the evidence became undeniable. The consensus is usually right, it is not always right, and the history of science is, in part, a history of questions that seemed closed turning out to be considerably more open than they appeared. Comet Maps is rounding the Sun this week. Active Region 4392, the same sunspot group that has been the subject of this entire story, has produced 4 M-class flares in 6 days and launched 3 coronal mass ejections currently in transit toward Earth. The temporal overlap between the comet's perihelion passage and the unusual productivity of this particular active region means nothing confirmed. There is no instrument currently deployed that could establish a causal link even if one existed. The tools for answering this question with the rigor science requires have not yet been built, and building them would require a level of coordinated long-term observational commitment that the field has not yet organised around this specific question. What we are left with is a notice coincidence in a week that is already dense with notice coincidences. A comet at its closest solar approach, a sunspot group firing repeatedly from disk centre, 3 stacked coronal mass ejections converging on Earth during the equinox window, and a question that the data cannot yet answer, hanging over all of it with the particular quality of questions that are too interesting to drop and too unresolved to settle. Is the Sun acting alone this week? Or is it responding to something larger than itself, something passing through its neighbourhood on a trajectory set long before any of this was being watched? We do not know, and that, depending on your disposition, is either the most frustrating sentence in this story or the most interesting one. Part 11. The Ohio fireball was not just background noise. On March 17, 2026, while space weather agencies were tracking the second coronal mass ejection, launched from active region 4392, and updating their arrival forecast for the compound storm sequence building toward Earth, something else was happening. Something faster, closer, and considerably more dramatic in the immediate human sense. A meteor, a rock that had been travelling through the solar system for an indeterminate period, measured in millions or billions of years, entered Earth's atmosphere over the American Midwest and exploded. It happened the way these events always happen, without warning, without announcement, without any of the ceremonial build-up that the scale of the event arguably deserved. One moment the sky over Ohio was ordinary, the next it was not. The fireball streaked across the atmosphere at tens of kilometers per second, compressing the air ahead of it into a superheated plasma sheath, glowing with an intensity that security cameras and dashcams across multiple states captured in the same moment of collective astonishment. Then it detonated, not on the ground, in the atmosphere, at altitude, where most meteors of significant size release their energy before the surviving fragments, if any, reach the surface. The force of the detonation was equivalent to several tons of TNT. The infrasound sensors, the network of low-frequency microphones maintained globally to detect exactly these kinds of atmospheric events, as well as nuclear tests, confirmed it. The object that produced this event was estimated at roughly 7 tons. This was not a shooting star. This was not the kind of thing you see on a clear night and make a wish about. This was a rock the size of a small vehicle, arriving at hypersonic velocity, and the atmosphere absorbed it the way a bulletproof vest absorbs a round, completely but not without effort. Reports came in from Ohio, Indiana, Pennsylvania, Michigan, and neighbouring states. People described a flash that turned night briefly into something resembling noon. The sonic boom arrived seconds after the light, rolling across communities that had no context for what they were hearing. Social media filled with dashcam clips and doorbell camera footage showing the streak and the flash from dozens of angles simultaneously. By the time infrasound analysts had confirmed the energy yield and the estimated object mass, the story was already circulating widely, and then, almost as quickly, fading, because the news cycle moves at its own pace, and a fireball that injures no one and leaves no crater is, in the current media environment, a 24-hour story at most. The coincidence with the solar storm sequence is precisely that, a coincidence. This needs to be said clearly and without hedging, because the temptation to connect these events into a single, unified narrative is powerful and understandable, and also physically unjustified. There is no mechanism connecting solar storms to an increase in Earth-crossing meteor activity. Coronal mass ejections are clouds of magnetized plasma. They do not gravitationally interact with asteroids in any meaningful way. Solar flares are bursts of electromagnetic radiation. They do not perturb the orbits of near-Earth objects. The Ohio fireball was on its own trajectory, following an orbital path determined by gravitational interactions that played out over timescales orders of magnitude longer than the 6 days active region. 4392 has been erupting. It arrived on its own schedule, indifferent to the solar wind conditions it passed through on the way in. The timing is remarkable in a narrative sense. It carries no physical significance in terms of causation. But here is what the Ohio fireball does, if you allow it to do its proper work rather than either over-interpreting it or dismissing it entirely. It refocuses attention on something that the daily texture of modern life allows most people to keep comfortably in the background most of the time. Earth is not sitting still in empty space. It is moving through a populated solar system at roughly 30 kilometers per second, sharing its orbital neighborhood with tens of thousands of catalogued near-Earth objects and potentially millions of uncatalogued ones, and the boundary between that neighborhood and the surface of this planet is not a wall. It is a membrane, a thin, continuous interface between the planet's surface and the rest of the solar system, through which material crosses regularly, quietly, and usually harmlessly, until occasionally it does not. Near-Earth objects are defined as asteroids and comets, whose orbits bring them into the vicinity of Earth's orbital path. The current catalogue maintained by NASA's Planetary Defense Program contains over 35,000 of them. That number sounds large and reassuring until you understand what it represents, the objects we have found. The catalogue is significantly incomplete at smaller sizes, particularly for objects in the range of 10 to 100 meters in diameter. This size range is important because it sits at a threshold, large enough to cause regional devastation if it strikes a populated area or generates a tsunami in an ocean impact, small enough to have largely evaded the sky surveys that have done an increasingly comprehensive job of cataloguing larger objects. We have found most of the civilization-threatening asteroids, the ones a kilometre or more in diameter that would cause global effects. We have found a smaller fraction of the city-threatening ones, and we have found a very small fraction of the Chelyabinsk-scale objects. The Chelyabinsk event of February 15, 2013, is the modern reference point for what this size range can do. A rocky object estimated at roughly 20 meters in diameter entered the atmosphere over Russia at approximately 19 kilometers per second and exploded at an altitude of around 30 kilometers with an energy release equivalent to roughly 500 kilotons of TNT, about 30 times the yield of the bomb dropped on Hiroshima. The shockwave shattered windows across a wide area. Over 1,600 people were injured, primarily by flying glass. Buildings were damaged, and the object was entirely undetected before it arrived. No warning, no preparation, no advance notice of any kind. It simply appeared in the atmosphere and exploded before any of the systems designed to watch for these things had any opportunity to see it coming. The Ohio fireball of March 17, 2026 was smaller than Chelyabinsk. It was estimated at roughly 7 tons, perhaps 2 to 3 meters in diameter, well below the Chelyabinsk object in scale. Its atmospheric detonation released less energy. It injured no one. But the physics that produced it are identical to the physics that produced Chelyabinsk, and to the physics that would produce something considerably larger if the object on the incoming trajectory happened to be considerably larger. The atmosphere does not sort incoming rocks by size before deciding whether to let them through. It receives whatever arrives. Close approaches, near-Earth objects passing within roughly 7.5 million kilometers of Earth, occur at a rate of several per week in the catalogue. Most are small, most attract. Most pass without public notice because they are neither large enough to be dangerous nor close enough to be visually remarkable. During the week of March 16th through 22nd, 2026, multiple catalogued near-Earth objects made close approaches on schedules that had been known to planetary defense tracking systems for months or years. Their arrivals were logged, their trajectories confirmed, their distances measured. Routine, in the specific sense that planetary defense work makes routine out of something that would have been considered extraordinary knowledge even 50 years ago. What is not routine is the density of notable events this particular week has accumulated. 3 coronal mass ejections from a single active sunspot, stacking up to produce a compound geomagnetic storm sequence during the weakest magnetic window of the year. A sun-grazing comet at perihelion, trailing a tail of ablated ancient material millions of kilometers long. A 7-ton fireball detonating over a populated American state with enough force to register on infrasound sensors across a wide area. Multiple catalogued asteroid close approaches proceeding on their indifferent schedules. None of these events individually crosses the threshold of unprecedented. Each of them has historical precedents, analogues in the record, reasonable scientific explanations that require no special pleading. But all of them together, in one week, in one solar system, around one planet, that clustering produces a feeling that is worth examining rather than either indulging or suppressing. The feeling is this: the solar system is not static backdrop. It is an active, dynamic, multi-body system in constant motion, with energetic events occurring on every scale from subatomic to planetary, on timescales from milliseconds to millions of years. Most of those events have no effect on Earth. Some do. The ones that do arrive without coordinating with each other, without announcing their intentions, without respecting the narrative convenience of arriving one at a time so we can process each one properly before the next. A rock that had been travelling through the solar system since before the first living cell divided on Earth arrived at this particular week and detonated over Ohio on the same day as the second solar eruption from active region 4392. It did not know that. It had no relationship to that eruption. The timing was coincidence in the fullest, most physically literal sense of the word. But the reminder it carries is not coincidental. It is structural. The boundary between Earth and space is a membrane, not a wall, and membranes by definition allow things to pass through. Space is not quiet right now. It is crowded, and it has always been crowded. We are simply paying attention this week in a way we do not always permit ourselves to do. Part 12. The growing problem of space traffic. 10,000 active satellites. Pause on that number for a moment, because it is easy to let it pass by the way large numbers often do. Acknowledged, processed, filed away without really landing. 10,000 objects, each one a functioning machine, moving through low and medium and high Earth orbit at velocities that make a rifle bullet look leisurely. The fastest of them, in low Earth orbit, complete a full loop around the planet in roughly 90 minutes. They are doing this continuously, day and night, in an environment that a sustained solar storm is currently in the process of heating, expanding and disturbing in ways that the operators of every single one of those 10,000 machines are actively monitoring right now. That number, 10,000, is not a ceiling. It is not a plateau. It is a waypoint on a trajectory that shows no sign of leveling off. Projections from multiple commercial launch providers, government space agencies, and independent aerospace analysts suggest the number of operational satellites in Earth orbit could reach 100,000 within a decade. 100,000. The driver is primarily commercial broadband, the deployment of large constellations designed to provide high-speed internet access to every point on Earth's surface, including the oceans and the polar regions and the remote territories where ground-based infrastructure has never reached. Each constellation requires hundreds to thousands of satellites to provide the coverage density and redundancy that makes the service commercially viable. Several such constellations are already partially deployed. Several more are in various stages of regulatory approval and launch preparation. The math of their combined ambition adds up to a near-Earth space environment that will be, within years, categorically different from anything that existed before. Tens of thousands of satellites moving in low Earth orbit at velocities of roughly 7.8 kilometers per second, in an environment that a sustained solar storm is currently heating and disturbing. The interaction between those two facts, the population density of the orbital environment and the physics of geomagnetic storms, is where this story becomes specifically and practically important rather than abstractly concerning. The atmospheric drag problem is not theoretical. It is operational, documented, and expensive. The clearest recent demonstration of this occurred in February 2022, when a geomagnetic storm, rated G1 to G2, the same range as the lower end of what the current sequence is forecast to produce, arrived shortly after SpaceX launched a batch of 80 Starlink satellites into their initial low deployment orbit. Newly launched satellites in these constellations are placed initially at low altitude and are designed to use their own propulsion to raise themselves to their operational orbit over the following weeks. During that low altitude phase, they are particularly vulnerable to elevated atmospheric drag because the air at lower altitudes is denser, and any expansion of the upper atmosphere makes it denser still. The February 2022 storm heated the upper atmosphere enough to increase its density at the satellite's deployment altitude significantly above the pre-launch models. The satellites, fighting increased drag with propulsion systems sized for normal atmospheric conditions, could not climb fast enough. 40 of the 80 satellites, exactly half the batch, lost the fight against the drag, fell below a survivable orbital threshold and deorbited. 40 satellites, representing tens of millions of dollars of hardware and launch cost, burned up in the atmosphere within days of their launch because a G1 to G2 storm arrived at the wrong moment in their deployment sequence. The current storm sequence is forecast to reach G2 to G3, with G3 peaks possible when the third coronal mass ejection arrives in alignment with the coronal hole high-speed stream. The satellites already operating in established constellations are in a stronger position than the newly launched ones lost in 2022. They are in stable operational orbits above the most vulnerable deployment altitude band, with propulsion systems that have been calibrated over months of operation and drag models that have been refined with real flight data. Their operators have been through solar storms before and know what to expect, but they are not immune. Every satellite in low Earth orbit experiences increased atmospheric drag during a geomagnetic storm because the storm's energy input heats the thermosphere, which expands upward, which increases the atmospheric density at any given altitude above the nominal baseline. Satellites that would normally need to fire their thrusters once every several weeks to maintain their orbital altitude may need to fire more frequently during a sustained storm period. This matters because propellant is finite. Every thruster firing consumes propellant that the satellite carries in a fixed quantity from the moment of launch. Propellant consumption determines operational lifetime. When the tank is empty, the satellite can no longer maintain its orbit and eventually deorbits. A geomagnetic storm does not destroy an established operational satellite the way it destroyed the newly launched Starlinks in 2022. What it does, more subtly and more cumulatively, is age every satellite in low Earth orbit by a small but measurable amount. It advances each one slightly toward the end of its operational life. Across a fleet of thousands of satellites, that collective aging has economic consequences that are real even if they are distributed across many operators and are difficult to attribute cleanly to any single storm event. The debris problem operates on a longer timescale but with more permanent implications. There are currently roughly 40,000 tracked pieces of space debris in Earth orbit, non-functional objects large enough to be detected and catalogued by ground-based radar and optical tracking systems. These include defunct satellites, spent rocket upper stages, fragments from on-orbit collisions and explosions, and hardware released during satellite deployments and spacewalks over the 60-plus years of human spaceflight. 40,000 tracked objects. And then, below the tracking threshold, hundreds of millions of smaller fragments, paint flakes, insulation material, metal shards, too small to track individually but large enough at orbital velocities to cause significant damage to an operational spacecraft on impact. During a geomagnetic storm, the same atmospheric heating that increases drag on operational satellites also increases drag on debris. But debris cannot respond. It cannot fire thrusters. It cannot compensate for the changed atmospheric conditions. Its orbital altitude changes at rates determined entirely by the storm's effect on the atmosphere, which differs from the pre-storm predictions fed into the conjunction analysis systems, the computational tools that calculate whether any two-tracked objects are going to pass dangerously close to each other. When the atmospheric conditions change faster than the models can update, conjunction analyses become less reliable. The safety margins that normally exist between predicted close approaches and actual object positions narrow in ways that are difficult to quantify in real time. Satellite operators receive conjunction warnings and must decide whether to maneuver based on probability estimates that are, during storm periods, less precise than they would normally be. The Kessler syndrome sits at the far end of this chain of consequences, and it deserves an honest description rather than either dismissal or dramatization. The scenario, first described by NASA scientist Donald Kessler in 1978, describes a cascade. A collision between two objects in orbit generates a debris field of fragments. Each fragment increases the probability of further collisions with other objects. Those collisions generate more fragments. The density of debris in the affected orbital region rises until the rate of new collisions becomes self-sustaining, until the debris field is generating new collisions faster than atmospheric drag is clearing old fragments. The result is an orbital altitude band that becomes effectively unusable for operational satellites for a period that, depending on the altitude, could extend to decades or centuries, because the debris at high enough altitudes takes that long to naturally deorbit. No one in the professional space debris community believes this cascade is imminent. The current debris density, while concerning and increasing, has not reached the threshold at which the self-sustaining collision rate becomes unavoidable. But the threshold is not infinitely far away, and it moves closer with every object added to orbit and every event that reduces the precision of the orbital predictions that keep operational satellites from colliding with the debris that surrounds them. Geomagnetic storms are one such event. Not the dominant driver of debris risk. The dominant driver is the sheer number of objects being launched, but a recurring perturbation that makes an already complex management problem measurably more difficult each time one occurs. The governance problem compounds the physical one. The global framework for managing orbital debris is fragmented in ways that reflect the geopolitical realities of space as a contested domain rather than the engineering requirements of managing a shared resource. Different national space agencies maintain different tracking catalogues with different coverage capabilities. Commercial operators are subject to different national licensing regimes with different debris mitigation requirements. There is no unified real-time authority with the mandate and the technical capability to manage orbital traffic the way air traffic control manages the global airspace, issuing clearances, coordinating maneuvers, maintaining separation standards across all operators simultaneously. When orbital density was low, this fragmentation was manageable. As density approaches the scales that current commercial ambitions imply, the absence of unified coordination becomes an increasingly serious structural vulnerability. The solar storm moving through Earth's orbital environment this week is a temporary disturbance. It will pass. The space weather will settle. Operators will step back from elevated monitoring. The atmosphere will cool and contract back toward its baseline density. Satellites will resume normal thruster schedules. The conjunction analysis systems will regain their normal precision as orbital predictions stabilize. But the population of objects in orbit will not decrease when the storm passes. The commercial deployment programs will not pause. The debris will not clear. The governance gap will not close on its own. The storm is a weather event in an environment that is simultaneously the most commercially valuable, most technologically critical, and most poorly governed shared space that humanity has ever created. The more we rely on space, the more fragile it becomes, and we are relying on it more every single day. Part 13, Artificial Intelligence versus Space Weather. There is a version of the future where AI sees the storm before we do, where machine learning systems trained on decades of satellite data, solar imagery, and magnetospheric readings pick up on patterns that human analysts miss. Subtle precursor signatures in the magnetic field configuration of an active region, anomalies in the solar wind density profile that precede a major eruption by hours, correlations between ionospheric behavior and incoming CME structure, that no human forecaster has had the bandwidth to notice across thousands of historical events simultaneously. In that future, the warning arrives earlier. The grid operators have more time to prepare. The satellite operators have more time to put their spacecraft into safe mode. The airlines have more time to reroute transpolar flights away from radiation exposure. Hours of additional lead time in the context of space weather is not a marginal improvement. It is the difference between a managed disruption and an unmanaged one, between a costly inconvenience and a cascading failure. That future is being actively built. Researchers at universities, national laboratories, and increasingly at commercial space weather companies are developing and testing machine learning approaches to solar storm forecasting with genuine scientific seriousness. The work is real, the progress is measurable, and the trajectory is encouraging. But there are specific, technical, non-trivial reasons why that future is not yet the present. And understanding those reasons tells you something important not just about AI, but about the nature of the problem it's trying to solve. Current operational solar storm forecasting is built on a foundation of physics-based models, computational simulations that attempt to reproduce the behavior of the solar corona, the solar wind, and Earth's magnetosphere using the equations of magnetohydrodynamics. Magnetohydrodynamics is the branch of physics that describes the behavior of electrically conducting fluids in the presence of magnetic fields. The solar corona is such a fluid. The solar wind is such a fluid. The plasma that fills the magnetosphere is such a fluid. Magnetohydrodynamic models treat these environments as continuous media governed by coupled equations describing mass, momentum, energy, and magnetic field evolution simultaneously, and they solve those equations numerically on computational grids that cover the space from the Sun's surface to beyond Earth's orbit. These models are impressive achievements. They can simulate the launch of a coronal mass ejection from the Sun's surface, track its propagation through the solar wind over the 1 to 3 day transit to Earth, and predict the resulting geomagnetic disturbance with skill that substantially exceeds random chance. They are the backbone of the forecasts issued by NOAA's Space Weather Prediction Center and equivalent agencies in Europe and Asia, but they are computationally expensive. Running a full simulation from solar surface to Earth in real time requires significant computing resources, and they have well-documented limitations that are understood by the researchers who build and use them. The most important limitation involves the internal magnetic field structure of coronal mass ejections, and specifically a quantity called BZ, the north-south component of the interplanetary magnetic field carried within the ejection. Whether BZ is pointing northward or southward when the ejection reaches Earth is the single most important factor in determining how severe the resulting geomagnetic storm becomes. A northward BZ deflects off Earth's magnetosphere. A southward BZ couples into it, opening a channel through which solar energy pours into the magnetospheric system and drives the ring current enhancement that produces geomagnetic storms. The difference between a northward and southward BZ arriving at Earth can be the difference between a minor disturbance and a major storm, between a G1 and a G4, and the physics-based models cannot reliably predict BZ orientation more than about 15 to 60 minutes in advance, which is approximately when the DSC-OVR satellite at the first Lagrange point actually measures it in the arriving solar wind. The forecast horizon for the most critical single parameter in space weather prediction is measured in minutes. Machine learning approaches are being applied to this problem and to others throughout the forecasting chain, and the results in specific domains are genuinely promising. Neural networks trained on historical solar imagery, photographs of the Sun's surface taken in extreme ultraviolet and X-ray wavelengths, have demonstrated the ability to identify active regions with elevated flare probability at accuracy levels comparable to experienced human forecasters. This matters because human forecasters can only examine so many images per day, while a trained neural network can process every image from every solar observatory in real time without fatigue or attention limits. Models trained on solar wind and geomagnetic data have shown the ability to predict KP index values several hours ahead, with skill scores that in controlled testing exceed the physics-based operational models. Recurrent neural networks, architectures specifically designed for sequential time series data, have shown capability in predicting the onset timing of substorms, the internal magnetospheric dynamics events that release stored energy into the atmosphere during geomagnetic storms. Each of these represents a real contribution to a field where better predictions have direct operational and economic value. The limitation that haunts all of these achievements is the same limitation that haunts machine learning across every domain where it is applied to rare, high-consequence events. The models are only as good as the data they were trained on. And the historical record of well-instrumented space weather events is, in the context of what the models need to learn, genuinely short. Comprehensive satellite-based solar observation began in earnest in the 1970s. Continuous, reliable solar wind measurements from spacecraft at the first Lagrange point, where Discover now operates, began in the 1980s. The period of overlapping, high-quality measurements across solar imagery, solar wind conditions, and geomagnetic response that would constitute an adequate training dataset is perhaps 40 to 50 years long. 40 to 50 years sounds substantial. It is 4 to 5 complete solar cycles. But consider what that training set contains, and more importantly, what it does not contain. It contains the 1989 Quebec storm, a genuine extreme event, KP of 9, province-wide blackout, one of the most significant space weather impacts of the satellite era. It contains the Halloween storms of 2003, a prolonged sequence of X-class flares and major coronal mass ejections that caused satellite anomalies, disrupted aviation, and produced aurora visible at unusually low latitudes. It contains the July 2012 event, a coronal mass ejection that, had it been launched in a slightly different direction 9 days earlier, would have struck Earth directly, and by some estimates could have produced a storm comparable to the Carrington event of 1859. That near miss is in the training data as a solar event. Its geomagnetic consequences are not, because it missed. What the training data does not contain is a direct Earth impact from a Carrington-scale event with modern instrumentation. The Carrington event itself, the most powerful geomagnetic storm in recorded history, which in 1859 set telegraph wires on fire, produced aurora visible at tropical latitudes, and would today be catastrophic for satellite operations and power grid infrastructure across wide geographic areas, occurred before any of the measurements that machine learning models are trained on. A model trained on the events of the last 40 to 50 years has never seen what a true extreme event looks like in the data, and a model that has never seen the extreme end of a distribution cannot be trusted to predict it when it arrives. It will extrapolate from what it knows. What it knows does not extend that far. The compound event problem is a version of the same issue applied to this specific week. Machine learning models have been trained on data that includes individual coronal mass ejections, CME-CME interaction events, equinox period storms, elevated background electron flux environments, coronal hole high-speed stream arrivals. Each of these phenomena exists somewhere in the training data, but the specific combination present this week, 3 interacting ejections from a disk center active region, arriving during the equinox amplification window with elevated background electron flux, followed by a coronal hole high-speed stream during solar maximum, may have no close analogue in the 40 to 50 years of comprehensive satellite measurement. A model trained on historical examples learns the relationships present in those examples. When it encounters a configuration that falls outside the region of its training distribution, a combination of factors that is genuinely novel, its output becomes less reliable precisely when reliability matters most. This is not a condemnation of artificial intelligence in space weather forecasting. It is an honest description of where the technology currently sits relative to the problem it is being asked to solve. The researchers developing these models understand these limitations. They publish papers that clearly describe the boundaries of their validation datasets and the caveats on their results. The forecasters at NOAA's Space Weather Prediction Center are using every available tool: physics-based simulations, machine learning aids, real-time solar wind measurements from DSCO-VR, expert judgment accumulated over decades of watching solar storms develop and evolve, and they are combining those tools with the professional honesty to communicate their uncertainty, rather than project false confidence. That uncertainty communication is itself a form of scientific integrity that deserves recognition rather than criticism. The gap between what AI can currently do in space weather forecasting and what the problem genuinely requires is not a gap of effort or intelligence or computational resources. It is a gap of data, specifically of rare extreme events that the historical record does not contain in sufficient quantity or diversity to train a model that can predict them reliably. Closing that gap requires either waiting for more extreme events to occur and be measured, which is not a satisfying strategy, or developing physics-informed machine learning approaches that embed theoretical understanding into the model architecture rather than relying entirely on pattern recognition from historical examples. That work is underway. It is producing results. It is not yet complete. The technology predicting this storm is genuinely impressive. It may not fully understand what it is predicting, but every storm it processes, every event it measures, every forecast it generates and has verified against reality makes it slightly more capable than it was before. It is learning. The question is whether it is learning fast enough. Part 14. The grid. Question nobody wants to answer. Here is a fact that power grid engineers know and very few people outside that profession ever stop to think about. The modern electrical grid is simultaneously the most sophisticated large engineering system ever built and one of the most geomagnetically vulnerable. Those two things are not in tension with each other. They are the same thing. The efficiency that makes the grid remarkable. Its ability to move enormous quantities of electrical power across thousands of kilometers with minimal loss, to balance supply and demand in real time across interconnected regions spanning entire continents, is structurally inseparable from the characteristics that make it susceptible to geomagnetic disturbance. You cannot have one without the other. The optimization that produces the capability produces the vulnerability as a necessary consequence. To understand why, you need one piece of physics that is not complicated but is fundamental. Faraday's law of induction states that a changing magnetic field in the vicinity of a conducting loop will induce an electrical current in that loop. This is not an exotic effect. It is the operating principle of every electrical generator ever built. Spin a coil of wire inside a magnetic field, change the orientation of the field relative to the coil, and current flows. The entire electrical civilization that powers the modern world runs on this one relationship between changing magnetic fields and conducting loops. It is the most practically consequential equation in the history of applied physics. During a geomagnetic storm, Earth's magnetic field fluctuates, not by a trivial amount. During a significant storm, the rate of change of the magnetic field at Earth's surface is large enough and fast enough to matter to conducting structures on the ground. And the high-voltage transmission grid is, from the perspective of electromagnetic physics, an enormous network of conducting loops. The transmission lines themselves, copper conductors strung between towers across hundreds and thousands of kilometers, form the sides of loops whose other sides are completed through the ground. When Earth's magnetic field fluctuates during a storm, these loops experience exactly the condition described by Faraday's law: a changing magnetic field, a conducting loop. The result is an induced current. These induced currents are called geomagnetically induced currents, and they have characteristics that are deeply problematic for grid infrastructure. They are not alternating at the grid frequency, not 60 Hz in North America, not 50 Hz elsewhere. They are quasi-direct currents, varying at frequencies far below what the grid is designed to handle, sometimes effectively static over periods of minutes. They flow through transmission lines and into the transformers at each end of those lines. And transformers, the critical components that step voltage up for long-distance transport and back down for local distribution, are not designed to handle direct current. They are designed with exquisite precision for alternating current at the grid frequency. Introducing direct current into a transformer designed for alternating current is not a minor perturbation. It is an assault on the device's fundamental operating principle. When geomagnetically induced current flows through a power transformer, it drives the transformer's magnetic core into a condition called saturation. In normal operation, the core is designed to respond to the alternating magnetic field produced by the alternating current flowing through the primary winding, transferring energy to the secondary winding through magnetic coupling. Saturation occurs when the magnetic field in the core becomes so strong that the core material can no longer respond proportionally. It has reached its magnetic capacity, and the relationship between current and magnetic field becomes nonlinear. A saturated transformer does several damaging things simultaneously. It draws vastly increased reactive power from the grid, power that circulates without doing useful work and that stresses every component in the connected system. It generates substantial heat internally, because the energy that should be efficiently transferred is instead being dissipated as thermal energy in the core and windings. And it produces harmonic currents, electrical noise at multiples of the grid frequency, that propagate through the connected transmission system and can trigger protective relays at substations that have no direct contact with the geomagnetically induced current source. This cascade of effects through protective relay systems is what produced the 1989 Quebec blackout, the most dramatic grid failure in the history of geomagnetic storms, and the event that forced the power industry to take space weather seriously as an operational concern. On March 13, 1989, a severe geomagnetic storm with a peak KP of 9, the maximum on the scale, a G5 event, hit the Hydro-Quebec transmission system. The geomagnetically induced currents saturated transformers. The saturated transformers produced reactive power surges. The reactive power surges triggered protective relays across the system, and the cascading relay trips collapsed the entire provincial grid in approximately 90 seconds. 6 million people lost power. The outage lasted 9 hours. The event caused hundreds of millions of dollars in economic damage and remains the defining case study in space weather infrastructure risk. 90 seconds. From normal operation to complete provincial blackout in 90 seconds, because a physical process 93 million miles away produced currents in copper wires that the protective systems interpreted as faults requiring immediate isolation. The speed of the cascade is one of the most important and least appreciated facts about grid vulnerability to geomagnetic storms. There is no slow degradation that operators can observe and respond to. There is normal operation, and then there is the cascade, and the time between them can be shorter than it takes to pick up a phone. But the Quebec event represents the acute scenario, the extreme storm, the rapid cascade, the dramatic and visible failure. The concern that keeps grid engineers in high-latitude countries awake at night during sustained moderate storms is different in character, and in some ways more insidious. It is the chronic heating problem. Large power transformers, the custom-built, extremely expensive, very difficult to replace units that anchor high-voltage substations, are thermal systems as well as electromagnetic ones. They operate within temperature ranges that their insulating systems are designed to handle. The insulating oil that fills the transformer tank and the paper insulation wrapped around the windings have temperature limits beyond which they degrade. Not instantaneously, thermally induced insulation degradation is a cumulative process, measured in the reduction of remaining operational life rather than immediate failure. When geomagnetically induced currents drive a large transformer into repeated saturation events over an extended storm period, not the 90-second cascade of Quebec, but a sustained 12, 18, 36-hour period of elevated geomagnetic activity, the cumulative heating effect on transformer insulation can be significant without producing any immediate visible symptom. The transformer continues to operate. The lights stay on. The readings from monitoring equipment may show nothing outside normal parameters, and somewhere inside the transformer tank, the insulating oil has been heated beyond its design range for long enough that its dielectric properties have been measurably degraded. The winding insulation has experienced thermal stress that has subtracted months or years from its expected operational life. The damage is invisible from outside. It will manifest later under ordinary operating conditions as a transformer failure that looks for all the world like normal equipment aging, because the forensic tools required to connect it to a storm event months earlier do not exist in routine utility maintenance practice. This is the replacement problem that infrastructure analysts find most concerning about extreme space weather scenarios. Large power transformers are not commodity items. They are custom engineered to the specifications of the substation they serve, manufactured in facilities with limited global capacity, and built on timescales measured in months to well over a year from order to installation. The United States has a limited domestic manufacturing base for the largest high-voltage transformer units. Many are imported primarily from manufacturers in Europe and Asia. If a significant geomagnetic storm damaged enough large transformers across a wide geographic area simultaneously, the queue for replacements would extend far beyond what the manufacturing capacity could address quickly. This is not a theoretical concern invented for disaster scenarios. It is a supply chain reality that the Department of Energy and the Federal Energy Regulatory Commission have explicitly identified in public documents as a critical infrastructure vulnerability. The grid is better protected than it was in 1989. That statement is true and important. Following the Quebec event, the power industry undertook substantial efforts to understand and mitigate geomagnetic storm vulnerability. Some utilities have installed neutral current blocking devices, hardware that interrupts the path through which geomagnetically induced currents enter transformer neutral connections, preventing the DC saturation effect while allowing normal AC operation to continue. Grid operators have developed storm operating procedures that include reducing transmission line loading during storm watches, positioning reactive power reserves strategically, and increasing real-time monitoring of transformer temperatures and reactive power consumption. Automatic protection systems have been recalibrated with space weather scenarios in mind. The North American Electric Reliability Corporation has issued standards requiring utilities to assess their geomagnetic storm vulnerability and develop mitigation plans. The industry is meaningfully better prepared than it was 35 years ago, but better prepared is not the same as fully protected. The infrastructure was designed for the normal operating environment, the conditions that prevail on the roughly 360 days per year when no significant geomagnetic storm is occurring. The engineering margins that exist in that infrastructure provide some buffer against storm conditions. Whether those margins are sufficient for a sustained 36-hour period of G2 to G3 geomagnetic activity with elevated geomagnetically induced current conditions across a broad geographic area simultaneously, the scenario that the current compound storm sequence could produce, is not a question that models answer definitively. It is a question that gets answered by observation in real time as the storm unfolds. The concern is not collapse, it is stress. Stress that accumulates invisibly inside equipment that looks fine from the outside. Stress that does not produce immediate failures but advances the timeline toward future ones. Stress that is distributed across a continent-spanning system in ways that no single monitoring point can fully characterize. The question that nobody in the power industry wants to be asked publicly, because there is no clean, reassuring answer to give, is not whether the grid will collapse during this storm. It almost certainly will not. The question is how much stress it will absorb over the next 48 hours, where that stress will concentrate, and what it will cost in equipment life and future reliability that we will not be able to measure until long after the aurora has faded and the news cycle has moved on. The grid operators are watching it in real time, with every tool available to them, doing exactly the job they were trained to do. The rest of us are waiting to hear how it went, and hoping that the margin was wide enough. Part 15. What if this is not the peak? We have spent 14 parts tracking a single sequence from a single sunspot group across a single week in the spring of 2026. That framing, the week as a unit of analysis, the sequence as a story with identifiable characters and a building plot, has been useful. It has given us a structure for understanding the physics, the timing, the compounding factors, the infrastructure implications. But the framing also contains an assumption that is worth pulling into the light and examining directly, because the assumption shapes everything about how we interpret what this week means. The assumption is that this week is a discrete event, something with a beginning, the first M-class flare from active region 4392 on March 16th, a middle, the stacking of 3 coronal mass ejections converging on Earth during the equinox window, and an end, some point in the coming days when the storms pass, the magnetosphere recovers, the all-clear assessments are issued, and things return to baseline. The assumption is that there is a baseline to return to, that after the event concludes, the story concludes with it. That assumption is understandable. It is how human beings naturally process time-bounded crises. We look for the arc, the resolution, the moment when normal resumes. It is also, in this case, physically incomplete, because the sun does not operate on story structure. It does not build to a climax and then resolve. It cycles, and we are currently near the peak of that cycle, which means the conditions that produce this week are not receding. They are the prevailing condition. Active region 4392 is still on the disk as of this writing. It is still classified as magnetically complex, still carrying the beta-gamma magnetic configuration that has made it so productive over the past 6 days. As it rotates toward the western limb over the coming days, the geometry of Earth-directed ejections will become less favourable. Plasma launched from a west limb position travels at an angle increasingly away from Earth's orbital path, reducing direct impact probability, but reducing is not eliminating, and the region may not be finished even as it rotates out of direct Earth-facing position. Sunspot regions can survive rotation around the Sun's far side. the hemisphere permanently invisible from Earth, and reappear on the eastern limb approximately 2 weeks later. Some regions make multiple transits across the Earth-facing disk before finally decaying. Active region 4392 has demonstrated across 6 days and 4 M-class flares that it is not a quiet region. Whether it survives its far-side transit and returns remains to be seen. The possibility is real enough that solar physicists will be watching its re-emergence window carefully. But active region 4392 is not the point. It is an illustration of the point. The point is that during solar maximum, the Sun does not have one active region. It has several, simultaneously, in various states of development and decay, distributed across its disk in positions that cycle through Earth-facing geometry on the roughly 25-day solar rotation period. Right now, while 4392 has been dominating the space weather narrative, other regions are present on the disk. Some are quiescent, some are producing minor flares. Any of them could develop the magnetic complexity that produces significant eruptions. The Sun's activity level, the overall rate at which it generates flares and coronal mass ejections, is not determined by any single region. It is determined by the phase of the solar cycle. And the phase of solar cycle 25 is maximum or very close to it. Solar cycle 25 has performed above the predictions that were made for it when it began its rise around 2020. Those predictions, based on models of the solar dynamo and historical cycle statistics, suggested a moderate cycle, perhaps comparable to the relatively weak cycle 24 that preceded it. The predictions were wrong in the direction of underestimation. Sunspot numbers have exceeded forecast values consistently. The rate of significant flare activity has been higher than anticipated. The cycle's maximum, whenever the smoothed monthly sunspot numbers confirm it in retrospect, solar maximum is always identified after the fact, not in real time, is shaping up to be meaningfully more active than the forecast baseline. We are living through a solar maximum that outperformed its own predictions, in a civilization that has built more space-dependent infrastructure than any previous generation, during a year that features 2 equinox windows in which the Russell-McFerran effect enhances geomagnetic storm coupling efficiency. The Russell-McFerran effect, which we covered in detail earlier in this series, is not a one-time event tied to the spring equinox of 2026. It is a recurring geometric feature of Earth's orbit, repeating twice per year with reliable precision. Every March, every September, the alignment of Earth's magnetic axis relative to the solar wind flow shifts into the configuration that most efficiently couples incoming solar energy into the magnetosphere. The enhanced coupling window that made this week particularly concerning will return in September, and solar maximum activity will likely still be elevated in September. The overlap between heightened solar productivity and heightened geomagnetic coupling efficiency is not a one-week phenomenon. It is a seasonal pattern that repeats twice annually for as long as the solar maximum persists. This means that the question to carry forward from this week is not whether the current storm sequence will be as bad as feared. That question will be answered by observation in the next 48 to 72 hours and will become historical record within days. The question to carry forward is structural. How many more weeks like this one are coming before the solar cycle descends from maximum toward the relative quiet of solar minimum? How many more times will an active region sit at disk center during an equinox window while a coronal whole high-speed stream reinforces an arriving CME sequence? The answer is not 0. The Sun will do this again. The only uncertainties are timing and magnitude. The 3 coronal mass ejections currently in transit will complete their journey. They will interact with Earth's magnetosphere, drive their geomagnetic storms, push the aurora to lower latitudes, stress the satellites and the grid and the navigation systems in the ways we have described, and then they will pass. The solar wind will return to something closer to background conditions, the magnetosphere will recover, the KP index will drop back toward quiet levels, space weather agencies will issue their all-clear notifications, satellite operators will stand down from elevated monitoring, power grid operators will return to normal procedures, the immediate crisis, such as it is, will resolve, and then the Sun will continue. It will build magnetic energy in the active regions that remain on its surface, and the new ones emerging from its interior through the convective layer. It will tangle field lines and store energy in topological configurations until those configurations become unstable and release. It will launch ejections in every direction, most of them missing Earth entirely, some of them grazing the magnetosphere at oblique angles, and some of them with the geometry and the timing aligned, hitting directly. It has been doing this for 4.6 billion years. The fossil record of geomagnetic storms is preserved in ice cores, in tree rings, in the remanent magnetization of ancient lake sediments. The Sun was doing this before the first multicellular organism existed. It will be doing this for roughly another 5 billion years, long after the last trace of human civilization has been recycled into the geology of a planet that will eventually be consumed by the star that sustained it. Every coronal mass ejection that has ever knocked out a satellite, disrupted a power grid, or painted the night sky with aurora that people 500 kilometers from their nearest neighbor looked up at in confusion and wonder. Every single one of those events was produced by a middle-aged star that has never once adjusted its behavior in response to what was happening on the third planet. The history of human civilization, every city constructed, every empire risen and fallen, every technological system developed from the first bronze tool to the 10,000 satellite orbital constellation, has unfolded entirely within the electromagnetic environment produced by this one star's activity cycle. We evolved under it. We built everything we have built under it. We have never experienced anything else. What is new is not the Sun's behavior. What is new is our sensitivity to it. Previous civilizations experienced geomagnetic storms as nothing more than unusual aurora and occasionally disrupted compass needles. They had no satellites to lose, no intercontinental transmission grids to stress, no GPS timing signals underpinning financial transaction systems, no orbital debris environment that becomes harder to manage when atmospheric drag models are disrupted. We have built all of those things. We have built them well and quickly and with extraordinary ingenuity. We have also built them in the electromagnetic environment of a star that will not change its behavior to accommodate them. We have increased our exposure to solar variability precisely by building the sophisticated systems that solar variability can disrupt. That is not an argument against building those systems. It is an argument for understanding the environment they operate in. This week is one data point. It sits inside a pattern that includes the weeks before it, the gradually rising solar activity of cycle 25's ascending phase, the previous storms, the previous equinox windows, and the weeks still to come before the cycle finally descends toward minimum and the Sun enters its quieter years. The pattern is the solar cycle. We are at its peak. And the peak does not end because one particular storm sequence has passed. The Sun is not finished. It is not close to finished. It has simply paused briefly between statements. This is not the event. This is the pattern. And we are only just beginning to understand how it behaves.